Welcome! In today's video I explain how to calculate a resistor for a LED.
To help you understand this properly, I'd start with some important basics. Please watch the entire video so that you can understand the secrets of LEDs and then calculate a series resistor in no time at all.
Let's get started.
With light bulbs it's easy. For example, a light bulb has an operating voltage of 16 volts. So we can simply connect it to a 16-volt power source. It doesn't matter whether we use direct or alternating current. The light bulb has an internal resistance. This regulates the current to the correct level.
A light bulb can therefore be compared to a resistor. LEDs require direct current and must be correctly polarized in order to light up. An LED has virtually no internal resistance and is therefore more comparable to a short circuit. This is also the reason why it breaks immediately when I connect it directly to the power source. The excessively high current destroys the LED. For light-emitting diodes, the maximum current is therefore specified for operation, for example 20 milliamps. The light bulb therefore requires a defined voltage. The LED requires a defined current. We must not exceed the values for either component. If we can reduce the values, we can dim the brightness of the components. But what is the voltage specification for the LED for? Let's stay with the topic of series resistors. To do this, however, we need to learn about a special feature of LEDs: forward voltage. To make LEDs light up, electrons are conducted through a semiconductor chip. There, they have to overcome the p-n junction. This is similar to jumping over a small ditch. This produces photons, in other words, light. In order for the electrons to cross the gap, they need a certain voltage, for example 2 volts for a yellow LED. The width of the gap is responsible for the different light colors of the LEDs. For example, a larger gap is needed for a blue LED. The forward voltage therefore increases to 3.4 volts. From video number 13 on Ohm's law, you are already familiar with my comparison of electricity with a bucket of water. The internal resistance of the light bulb regulates the current to the correct level. The LED is like a step that the water has to flow over. In the previous example, we had our trench that the electrons had to jump over. This is now our step. If the voltage is too low, no current flows and the LED does not light up. If the voltage is higher, current flows but in an uncontrolled manner. The current is almost always too high and the LED is destroyed. You can try to find exactly the right voltage level, but in most cases this is not practical. Due to component tolerances between different LEDs, the steps are also of different heights. As a result, even small changes in the operating voltage can destroy the LEDs. The simplest method of controlling the different currents is to use series resistors. The forward voltage specification is therefore not an operating voltage, but rather the voltage that drops across the LED when it is operated at the correct current. And it is precisely this forward voltage that is specified for LEDs in the datasheet. We connect incandescent bulbs in parallel to a fixed operating voltage. A fixed operating voltage is not a good solution for LEDs. The current can only be set appropriately with series resistors. Here are a few more circuit examples for connecting light-emitting diodes incorrectly and correctly. The LED and the series resistor share the operating voltage. The forward voltage drops across the light-emitting diode. The remaining voltage drops across the resistor. So we can simply subtract the forward voltage from the operating voltage. The result is the voltage across the resistor. We calculate 16 volts minus 2 volts, which equals 14 volts. Using Ohm's law, R equals U divided by I, we can now easily set any current strength at the LED. For example, 20 milliamps. However, in the equation we have to calculate in amps, this means 0.02 amps. We calculate 14 volts divided by 0.02 amperes equals 700 ohms. In order not to overload the resistor, we also have to calculate its power in watts, using the formula P equals U times I. 14 volts times 0.02 amps equals 0.28 watts. So the correct resistor has 700 ohms and consumes 0.28 watts. Now we will find that not every resistor is necessarily available. For example, in the E12 standard series, there do not exist a 700 ohm resistor, only 680 ohms or 820 ohms. To avoid overloading the LED, I can only use the next larger value. In this case, that would be 820 ohms. Using Ohm's law, we can now also calculate the current at 820 ohms. I equals U divided by R. 14 volts divided by 820 ohms equals 0.017 amps, or converted 17 milliamps. At 14 volts and 0.017 amps, a power of 0.238 watts is generated at the resistor. Resistors can become very hot during operation. Therefore, I recommend only using them at a maximum of about 70% of their capacity. A resistor with a quarter watt, this means 0.25 watts, is therefore a little too low for our application. I prefer to use a stronger resistor with 1 watt of power. I have set up our calculation example here. Our operating voltage is 16 volts. Our forward voltage of about 2 volts drops at the LED. The rest of about 14 volts drops across the 820 ohm resistor. As expected, the current is now 0.017 amps. The 1 watt resistor does not get too hot. I like to test this as follows. If I can still touch it for 1 minute without burning myself, then everything is okay. You may have already noticed that the measurements on the LED or resistor are not always completely accurate. You must take these component tolerances into account when building your circuit. It may be wise not to always use the maximum current of the LED. For example, if the LED is rated at 20 milliamps, you can also set it to 18 milliamps. It will still shine brightly enough. If there are any unexpected fluctuations in the circuit, you will still have some reserve and the LED will not break. A lower current also increases the working lifetime of the LED. By the way, it does not matter whether the series resistor is installed before or after the LED. In both cases, the series connection reduces the current to the correct level. The voltage drop across the series resistor should be at least approximately 3 volts or higher. If the voltage here is set too low, the current at the LED can easily be exceeded as soon as the supply voltage deviates slightly. I have various LEDs here. You can get all of these in our online shop, as well as suitable series resistors. If there is no datasheet available for such LEDs, you can assume that they can all withstand at least 20 milliamps. I will also list the typical forward voltages of the different light colors here. If you don't have the right resistor to hand, you can connect several resistors together to obtain the desired value. For example, if you connect two 1000 ohm resistors in series, this adds up to 2000 ohms. Two 1000 ohm resistors connected in parallel add up to 500 ohms.
We also stock these street lights for model making. Although these lights can also handle 20 mA, they are usually much too bright for the ambience in model making. Something like 5 mA is more suitable. As long as you don't exceed 20 mA, you can simply try out different series resistors until you find the brightness you like. For model making, I recommend an inexpensive 12-volt transformer with direct current and furniture approval. This means it can also be mounted on wood. There, you simply connect each LED individually with its own series resistor. Each series resistor consumes energy in the form of heat. If you only install a few LEDs, this is hardly significant. Each individual LED requires about 0.24 watts of power. However, an LED strip has an extremely large number of LEDs, so it makes sense to keep the losses at the resistors as low as possible in order to save energy. If, for example, I connect 3 LEDs in series, the power consumption per LED drops to 0.08 watts. This saves us an enormous amount of energy. Let's calculate why this is the case. To calculate the voltage drop across the resistor, I have to subtract the forward voltages of all 3 LEDs in the series connection. So I calculate 12 volts minus 3.2 minus 3.2 minus 3.2 volts and get 2.4 volts at the resistor. You then calculate the resistance in the same way as you have already learned. For 20 mA, this results in a resistance of 120 ohms. A power of 0.048 watts is dropped across the resistor. We have just calculated the power at the resistor. However, to determine the energy consumption, we need to calculate the power of the entire circuit. P equals U times I. 12 volts times 0.02 amperes equals 0.24 watts. This consumption is the same for both circuits. However, we are operating 3 LEDs in series. Therefore, we only use 1/3 of the power per LED, that is 0.08 watts per LED. We have learned a lot today about LEDs and series resistors, and if you enjoyed it, please subscribe to the channel. This really helps us to produce more videos like this. Thank you for watching, see you next time.